Good day, students. It's class time. Watch lessons in real time on the Television Jamaica YouTube channel or One Spot Media. We also are live on gojamaica.com. If you have questions on today's subjects, you can send them to the Television Jamaica's Facebook page at Television Jamaica or Instagram at television_Jamaica or use the hashtag TVJClassTime. I am Devalian Green, and with me is Sean Myers, and we will be guiding you through CSEC Industrial Education this week. All right, we are going to be looking at semiconductors. All right? Now, as students of electrical technology, right, we would have established the knowledge of what are conductors, right, and also what are insulators. Based on your prior knowledge, you would have known that a conductor is a material which permits the flow of electricity, while on the other hand, an insulator is a material which resists this flow. Now you may be thinking, what is a semiconductor? Right? In order for us to understand the concept behind this, let us look a little at the electron theory of semiconductors. Right? We will also be guiding you along, and there are certain key terminologies that you must understand in order for you to keep up. All right? So, what are semiconductors? Right? A semiconductor, this is a substance which possesses a resistance level between that of a conductor and that of an insulator. Right? Now, as we mentioned earlier, we talked about the atomic structure, the electron theory behind semiconductors. Now, based on the topic or your prior knowledge, you would have known that a conductor, right, is a material which on its outermost shell, right, we're talking about the atoms. On the outermost shell, which makes up a conductor, it has less than 3 electrons, right? If it has 1 electron, it is considered a good conductor. If it has 3 electrons on its outermost shell, it is considered a poor conductor. On the other hand, with insulators, these have more than 5 electrons on its outermost shell, right? If it possesses 8 electrons on its outermost shell, which would be its maximum capacity, it is considered to be a very good insulator, right? If it has 5 electrons, it is considered a poor insulator. Now, for semiconductors, these materials have 4 electrons on its outermost shell. So therefore, it is in between that of a conductor and that of an insulator. Mr. Myers?
All right, really want to say thanks to you, Mr. Green, for giving our students an overview of what we're going to be discussing today. Now, as we look at our slide, you know, there are certain terminologies that we're going to be using today, students. There are certain terminologies that we're going to be using. So one of the terminology is a crystal lattice structure. That is one thing that you're going to be coming across. So these are things that you want to write down. The definition for these things are very important to CXC, because as you are going to be talking about, you know, semiconductors, then these terminologies are very, very, very vital. So the crystal lattice structure, what is it? When we talk about covalent bonding, that's another terminology. Intrinsic, extrinsic semiconductors, doping agent, dopant. Another terminology that we're going to be using is impurities, majority carriers, minority carriers, holes, electrons, donor, acceptors. Now, these are things that you will be hearing us referring to as we go through our presentation. Now, as we go through our presentation and these words come up, then you want to take note of the definitions for these words. Now, as Mr. Green said earlier, in order for us to understand semiconductor, then we must go back to the theory of electrons, the electron theory. Now join me as I go on the board over here. And I'm just going to put a little simple atomic structure on the board. Now one thing with electrical, we are concerned about the outermost shell, which is the valence shell. Now as Mr. Green mentioned, if we have 3 electrons on the outermost shell, then we realize that the material that we're speaking to is a good conductor of electricity. It's a conductor of electricity. Mr. Green went about, highlighting that if it just have 1, then it would be a very good conductor. If it has 3, then it's a poor conductor. Now, when this outermost shell has 4 electrons, then that is what we're going to be talking about today, semiconductors. And that is where, our topic comes from, when it has 4 electrons on its outermost shell. Now, if it has more than 4, then we are now moving into the capacity of speaking about what an insulator is. So we understand, students, where the term semiconductors come from. Now, semiconductors, as was mentioned earlier, it only has 4 electrons on its outermost shell. It is midway between that of a conductor and that of an insulator. It is midway between that of a conductor and that of an insulator. If we look on our chart, you notice there that we have a resistivity chart. And when you look at the conductors on a resistivity chart, like silver, gold, and carbon, then it has a very poor, it's times 10 to the negative 8. That is the resistivity, because these are materials that allow current to actually flow easily through them. Then if you look at, times 10 to the 2, times 10 to the 4, like silicon and germanium, which are commonly used semiconductor materials, then you realize that it is midway. And then if you move on into the higher categories now, like times 10 to the 10, times 10 to the 14, times 10 to the 18, then this is where now we're speaking about our insulators. And good insulators are like glass and quartz and rubber and so forth. Now, I'm going to ask Mr. Green to go through with you an explanation now of some of our most commonly used semiconductor materials. So what are some examples, Mr. Green, of some semiconductor materials?
Now, once we start referring to semiconductor materials, right, some of the most commonly used are silicon, right? You have germanium, and you also have what we call gallium arsenide, all right? These are well-known materials that are used for semiconductor purposes, all right? Now, let's take a look at silicon. Now, silicon is obtained from silica, and as you hear that term, you should be thinking of sand, right? Now, it has what we consider to be a high resistance to voltages and temperatures, right? All right, its temperature and resistance does not change much when it is heated, and that is very key to note, as you know that, or what we will be discussing, temperature does have an effect on semiconductor materials, all right? Now, its potential barrier is about 0.6 volts, all right? Now, let's look at germanium, right? Germanium is obtained as a byproduct from the flue dust of the zinc industry, all right? And the electrical conductivity of germanium is higher than that of silicon, right? And it has more optical characteristics, right? The potential barrier is also smaller than that of silicon, for it is about 0.2 volts as it relates to germanium.
All right, so thank you very much for that, Mr. Green. Now, as we move on, we're going to be looking at, the arrangement of our semiconductor materials. Now, our semiconductor materials, as Mr. Green mentioned earlier, silicon and germanium, they are arranged in what is called a crystal lattice structure. And atoms, it occupies sites at the nodes of the lattice. Now, as we look at, the examples of our semiconductor, the categories that they fall into, then we have 2 categories. We have intrinsic semiconductors, and we have extrinsic semiconductors. Those are the 2 broad categories that they fall into. Now, students, as we mentioned, it is very important that you take note of these definitions So an intrinsic semiconductor material is actually a pure semiconductor. That means it is only made up of silicon. It is only made up of germanium. So it is free from any impurities. But we're going to realize that there are challenges with it. It is not workable. We're going to be realizing that as we go along. So as a result, now it moves us now to our extrinsic semiconductor material. Now extrinsic semiconductor material is where you actually add impurities to it to ensure that it is workable. It can conduct electricity. Now some examples of our extrinsic semiconductor materials are our N-type semiconductor and our P-type semiconductor. And the aim of our discussion today, we're going to be hoping that we can draw the crystal lattice structure, because we don't want to just be presenting information to you students. We want for you to be able to retain the information. So we'd like for you to be able to draw the crystal lattice structure, and we're going to be having a discussion now as to how we come up with the N-type and how we come up with the P-type semiconductor material. But let us focus a little on our first, which is the intrinsic semiconductor. Now let us talk a little bit about our intrinsic semiconductor. Now our intrinsic semiconductor, we mentioned that you have interatomic spacing. And these interatomic spacing, it actually occupies, you know, the shells, the outer shells, the valence shell of the atomic structure that we mentioned about. Now these linkages form what is called covalent bonds. And these are formed at the outermost shell. Now as we looked at our atomic structure earlier, we realized that semiconductor materials actually has 4 electrons on its outermost shell. Now from your chemistry class, you know that in order for the shell to be complete, then it needs to have 8 electrons there. It needs to have 8 electrons. But there's a beauty about a semiconductor material. Since it only has 4, then it is not going to be giving up any electrons, and it is not going to be readily accepting any electrons. And that is why it is so hard to work with intrinsic semiconductor materials. Now, covalent bonds, a very important terminology. These are forms when individual atoms share electrons of their neighbors. So that is what covalent bonding is, students, where you have individual atoms sharing the electrons of its neighbors. It's very important to note that the number of holes is going to be equal to the number of electrons. Now, as we look at this slide that you're seeing, we can realize there the covalent bonds that we're talking about. So silicon atom, you notice that the atomic number is what, 14? And it has 4 electrons on its outermost shell. But we are not so concerned about the atomic number. There is no need for you to, you can just save that, for future reference. But in electrical, we're not so much concerned about the atomic number. What we are concerned about is what is happening on the outermost shell, the valence shell. So it has 4 electrons on this valence shell. And when we come back, we're going to be speaking to you a little bit more about the intrinsic semiconductor.
All right, we're going to pause right here and take a quick break. All right, stay with us. We will be back.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching. Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.
All right, welcome back. And we are going to be continuing our lesson. Now, Mr. Myers will be picking up where he left off.
All right, so we're talking about covalent bonds, students. That's what we're talking about, covalent bonds. Now, if we move back to our PowerPoint slide, then you realize there that we have the silicon atom that we were speaking about earlier. And our silicon atom, you realize where covalent bonds are coming from. So when we zoom in, you're going to be drawing this lattice structure very soon. So I encourage you please to get out your pens and your papers and your pencils, because we want to ensure that you retain the information that we're referring to. So when you zoom in, you notice there that covalent bonds are identified. So we have 4 electrons on its outermost shell, but the one that is in the center, then it is picking up 4 electrons from its neighbors. And that is what covalent bonding speaks to, the sharing of electrons. Now, this is what happens in an intrinsic semiconductor. But as we mentioned to you, there's a big problem when it comes to the intrinsic semiconductor. The conductivity is too low for most purposes. So it's hard to work with. We can't really do much with it. And that is the reason why now we have to move on to the next type of semiconductor that we have, which is actually the extrinsic semiconductor. Now, with the extrinsic semiconductor, it's not that we have a different material working it with. It is the same silicon, it's the same germanium, but in order for us to actually make it workable, then what we have to do is to add small amount of impurities to that pure material. Small amount of impurities. Now on our slide, you notice that there's the next terminology that we come across, which is doping. And that is what doping is, students. Just adding small amount of impurities to that pure semiconductor. But here's the question. Where will you get the material from to add to the pure semiconductor? Where would you get the dopant from? Well, as we mentioned earlier, that the semiconductor, silicon, germanium, these are group 4 elements. They're group 4 elements. So in order for us to get the impurities, then the impurities have to come from a neighboring element. So the neighboring element to a group 3 is actually the neighboring element to a group 4 is actually the group 3 and the group 5. And that is where we'll be getting, the impurities from. Now what we're going to be doing is that we're going to be moving to our board. And we're going to be going about drawing, our first intrinsic semiconductor material. Let us see if we can carry out that activity together. Let us draw our intrinsic semiconductor material. So that is what we're going to be doing. We're going to be drawing our intrinsic semiconductor material. Now, as we mentioned earlier, our intrinsic is a plus 4e element. And let us say that we're just going to be utilizing a few of them. So all of these are plus 4e, plus 4e. Now, we mentioned earlier that you have covalent bonds. So let us put in our crystal lattice structure linkages right here. So these are linkages, students. All that we have in blue there, those are our linkages. We missed one right here, so let us just put that in. Now we're going to be getting a different color. And what we're going to be doing now is to show you how we actually get our electrons in. So let us use the one that is in the center first. So this, as we mentioned, has 4 electrons. So one there, one there, one there, and we have an electron right here. So you notice it has 4 electrons that makes up, the silicon atom. But if we note this one right here, then it is also going to have an electron here. It will have another electron right here, one there, and one that is there. That is how it will get its 4. But if you notice that this electron that we have right here, it belongs to the silicon atom. But it is now doing what? Sharing And in the same process, this silicon atom is also sharing. So as a result of the sharing, then we will have now all shells participating in what is called covalent bonding, which is a sharing of electrons. So that is what we will have. So this is now an intrinsic semiconductor material, free from any impurities. And we missed out our plus 4E right here. So let us zoom in on our board now, students, and see if we can understand our intrinsic semiconductor material right here. So you notice plus 4E, pure silicon. This is a crystal lattice structure that we're talking about. And we have covalent bonding taking place. Pure intrinsic semiconductor material. Now if we move over back to our PowerPoint presentation, then on our PowerPoint presentation, you notice that we actually move over to an extrinsic, where we add an impurity to the crystal lattice structure of the silicon. So the impurity came from a group 5 element, and that impurity is actually antimony. It has 5 electrons on its outermost shell. Now if we should actually go back to our board, and on our board, let us say that we're going to be removing one of these silicon atoms, and we're going to be adding what is now a plus 5 element. Let us now add our plus 5 element to our board. That is what we now have right there. We add our plus 5 element. Now remember, we would have 1, 2, 3, 4. All right? So we'll have 1, 2, 3, 4. This would have been here from earlier. So that would have come from that element over there. So we have 1, 2, 3, 4. But what is missing? We have one more element, which is a 5th element. So this is an element which is free. This is now we now have a free electron. That is now we have a free electron. And that electron now is able to actually wander about in this crystal lattice structure, bouncing other electrons out of their place. Now remember, from our studies of electricity, the movement of electrons is what current is. The movement of electrons. So this free electron, it is able to move here, knock this one out of place, this one is able to move, and it is wandering about in the crystal lattice structure. Now, for a semiconductor material, we could dope it with a few other, group 5 elements, and as a result of doping it with a few other group 5 elements, then you realize that what we will now have here is that it would have, 2 or 3 free electrons moving about, wandering about. And then as a result, now we're able to actually work with that structure. Now, this is now an extrinsic semiconductor material. Now, let us now move back to our PowerPoint presentation there. And we're going to ask Mr. Green to actually take you through a discussion now to identify the free electron right there on our board as we move over to drawing the P-type semiconductor on our whiteboard. Mr. Green.
All right. So as was discussed by Mr. Myers earlier, right, you would have looked at what are intrinsic semiconductors, and he just discussed the extrinsic semiconductor, in which you would then add a doping element, right? You would take an element from either the group 3 or the group 5, right? Now, in the previously mentioned process of doping, he added a group 5 element, right? Which is antimony. Now, what you have happening is that based on the amount of electrons that is within or which is upon the outermost shell of the antimony atom, you would have the resulting free electron without a bond, right? Now, this free electron is now able to roam. And as Mr. Myers mentioned, and as you would have known, based on the electron theory, that the movement of electrons is what causes our current, all right? Now, this would cause what we call a N-type semiconductor, because what you have occurring is that the electron would become now our majority carrier. Now it is negatively charged, right? Electrons are negatively charged. So that would give us our terminology or category, the N-type semiconductor. Now we'll be moving on to another method of doping with Mr. Myers. All right?
All right, so we're still at our extrinsic semiconductor. And now we're going to be focusing on our p-type. So we're going to be looking at our p-type, and we're going to be drawing our atomic structure, or crystal lattice structure for our p-type semiconductor material. Now, as we mentioned earlier, we have our crystal lattice structure. We have our crystal lattice structure. And we also have the covalent bonds being formed, which is the sharing of electrons. Now, in order for us to actually benefit from the p-type, remember, we're going to be doping with a group 3 element. And an example of a group 3 element is actually boron. So we're going to be doping with a group 3 element. So we know that right here, we're going to have a plus 3e element, which is going to be our group 3 element. Now, for it to have plus 3e, then we're going to have one electron right here, one there, and we're going to be having another electron right there. But for right here, we're going to be having what we call a hole, because that is going to be void. Because since it is boron, we will only have what? 3 electrons. Now, for our silicon, remember we're still having a silicon structure here, so it's plus 4e. We're going to be having one electron there, one will be there, one will be there, one will be there. But then now the other shells will be filled out with neighboring electrons. So we can safely put in the other electrons because we know that they're going to be sharing electrons from their neighbors. So plus 4, plus 4. So this is our crystal lattice structure. So we actually hope, students, that you're actually drawing this structure. It's a little bit tedious to draw, and you have to be doing it over and over. But let us see if we can actually zoom in, because the crystal lattice structure for p-type is different from that of the n-type. For the n-type that we mentioned earlier, you had the plus 5e element, you have a free electron wandering about. But for this structure, you notice we have a what? Plus 4e. So we're doping the silicon with boron. Boron comes from a group 3 element, so it has 3 electrons on its outer shell. Now, having the 3 electrons, then what we realize here is that we have a what? A hole. We have a hole. Now, we refer to this hole as being positively charged. So the majority carriers in a p-type semiconductor, majority carriers would be what? Holes. So the majority carriers would be holes, and the minority carriers would be electrons. And we're going to be focusing on that a little bit later in our slides. So the majority carriers will be holes, and the minority carriers will be electrons. So this hole that we have right here, how will it actually affect our entire crystal lattice structure? How will we be able to get the movement of electrons taking place? Now, over the years, we have had a lot of debates about the holes moving. But one thing I want you to bear in mind is that the hole never moves. So this hole, it is positively charged. It's a p hole. It is always positively charged. So the electron is going to be attracted because the electron is negatively charged. So the electron will be attracted to the what? The p hole. And as a result, this electron that we have right here will actually take the space right there. So let us do that. This electron that we have right here will actually move and take the space right there. So when it takes the space right there, then what is going to be happening? it will now create a what?
hole.
A hole on this side. So it would appear to the naked eye as if the hole actually what? Moved. But in truth and in fact, what moved was the what? The electron. So this hole is right here. You could have an electron that is all the way up here that would actually be what? Attracted to this positive hole. And then now the electron could jump from its shell and come right there, and it just creates a what? A hole. So as a result of that, we realize now that we're actually moving. Electron is actually moving from one point to the next. So this is a crystal lattice structure, and it is very, sometimes tedious to draw. But if you go through the exercise of drawing its students, then you get to familiarize yourself with doping. You get to familiarize yourself with, the covalent bonding that is taking place. And you get to familiarize yourself with also the electrons and the holes, the majority charge carriers and the minority charge carriers. Now, if you look back at our PowerPoint, our slide, then we realize our hole right there. So boron, we have the silicon structure. And we realize that, we have the hole that is actually free, and electrons can actually jump and, jump into that space. And as a result, you will have a space created elsewhere. So we have electrons that is actually moving. So just to reemphasize what we mentioned earlier, the p-type semiconductor, majority carriers are holes, the minority carriers are electrons. And when we look at the n-type, we actually have majority carriers being electrons and the minority carriers being holes. Now what we're going to be doing is actually look at our p-n junction. That is what we're going to be doing. Now I'm going to allow Mr. Green to actually speak to you a little bit about our p-n junction.
All right. So when we are referring to what we call a p-n junction, right, this arises when we take one p-type semiconductor and we will combine it or put it next to what we call the n-type semiconductor. Now, between these two materials, we will have forming the junction, the p-n junction, all right? And you're going to be realizing that based on the composition, right, of these two materials, there's going to be some activity taking place as a result of our majority carriers on both sides. As was before mentioned by Mr. Myers, for the p-type semiconductor, our majority carriers are the holes, right? The holes are positively charged. And for the n-type semiconductor, we have our majority carriers being our electrons, which are negatively charged. And based on your knowledge, you would realize that positive and negative, right, unlike poles or unlike charges, will be attracted, right? So this is what is going to be causing a phenomenon at our p-n junction. And now Mr. Myers will be giving you a bit more information as it relates to the p-n junction.
All right. Now, we want to just quickly put on the board, students, what will be happening when we actually fuse a p-type and fuse an n-type together. So we know the p-type is positively charged, so we're going to be using these, holes to actually refer to our positively charged p-type. And we know that our, this is our p-type. And then we have our n-type. And that is where we actually end up with our what? p-n junction. That is where we end up with our p-n junction. So these are electrons that we're going to be having over here, and our electrons. Now, right across this barrier, we realize that we will have, this is where they fuse. This is where they fuse. So across where they're fused, we refer to it as a junction. But right across our junction, what we will have naturally taking place is actually space charges. So over here, we have an increase in holes rather. These are positively charged. So what we will realize is that these positive charges will just wander over to where our electrons are, because they have the laws of attraction taking place. And then now we will have these negative charges wandering over to where our p-type is, because we have, attraction taking place. But students, our time is going a little with us. So what we're going to be doing is to encourage you to read up on these things. And, we are going to be looking forward to see you again in the near future.
All right. So that is it for our CSEC Industrial Education lesson. And up next, we have CSEC POB. So stay with us. We'll be right back.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.
Good day, students. Welcome back to class time. I'm Georgetta Thomas Legister, your CSEC Principles of Business teacher for this session. And today, we will be looking at logistics and supply chain. So get your book and a pen, and let's get started. Now, before we get into our lesson, let us examine the objectives we will be looking at today. So at the end of the lesson, we hope to achieve these objectives. So one, to explain the terms logistics and supply chain operations. Next, to describe the links in the distribution chain. To discuss the components of logistics and their roles. To outline various modes of transportation, and to explore the impact of logistics on competitiveness. So think about it. You have heard the term logistics before, but what is logistics really? Think about it, and I want you to write a definition of logistics, your own definition of the term logistics. Now, when you pass an 18-wheeler on the highway, when you shop in your local grocery store, when you collect a package at your door from Amazon.com, you are indeed having a logistics moment. So let us look at what logistics is. But before we go there, let me share one of my favorite logistics quotes. The line between order and disorder lies in logistics. Sun Tzu, a Chinese military general. Now you might be wondering, logistics, military, what is this all about? What's the connection? Now, a little history of logistics. The term logistics derived from military activities during World War II and then gradually spread to the business world. So what we will focus on is business logistics. Now, what is logistics? Now, logistics may be defined as a process of planning, implementing, and controlling the efficient, cost-effective flow and storage of raw materials, semi-finished goods, and related information from the point of origin to the point of consumption for the purpose of conforming to customers' requirements. Now, I know that's a mouthful, but as we go through, we'll understand more when we look at the different aspects related to logistics. Now, logistics is closely related to marketing. That's the lesson we looked at last time. So there will be some familiar terms and some new terms that you will learn today. Now, what is supply chain operations? When you hear of the supply chain, what comes to mind? Now, the supply chain is really a network between a company and its suppliers to produce and distribute a specific product. Now, there are basically 4 interrelated operations in the supply chain, and we looked at those when you were introduced to marketing. So, any idea what those interrelated operations are? I'm sure you know them. So we have the producer or the manufacturer, the wholesaler, the retailer, and the consumer. Now, the supply chain represents the steps taken to get the product or service to the customer. A supply chain shows the flow of information and materials across an organization. Now we will be looking at some key components of logistics. There are a number of components that are related to logistics. Now, for the purpose of this lesson, we will focus on 4 of these components. Any idea what these components are? All right, write them down and compare with what we will discuss. Great. Now, we'll be looking at procurement, inventory management. Can you guess what the other is? Transportation and warehousing. As I said, these are the key components. There are others, but for the purpose of this lesson, we will focus on these 4. So let us look at procurement. When you hear the term procurement, what comes to your mind? And for most people, when they hear procurement, purchasing comes to mind. But procurement is a little more than just purchasing. It's basically the steps or the process that you have to go through in order to make that purchase. Remember, we're looking at it from the point of view of a business and not an individual standpoint, right? So when looking at products and prices, procurement is considered, right? Now, procurement is a process of finding, agreeing on terms and conditions, and acquiring goods, services, or work from an external source. Now, the process is used to ensure that the buyer receives goods, services, or work at the best possible price when a number of factors are considered. Factors such as quality, quantity, time, and we're talking about time of delivery, time a job will take to be completed, location, and other aspects are compared. So most business will have what you call a procurement committee. So this is a group of persons, mostly drawn from different departments in the business, who sit together and go through quotations from different suppliers. So you're looking at things such as price, as I said earlier, the quality that the products will be made from, how soon will the products be delivered, what quantity do they have available. And you look at all these aspects. Of course, the cost is also a crucial factor, but it cannot be the only factor. Now, the procurement committee would then decide which supplier gets the job, which supplier we actually buy goods from, right? Now, inventory. Have you ever heard the term inventory before? What comes to mind when you hear the term inventory? Right. So inventory is basically stock that the business holds, goods that you hold for resale. The business hold for resale, right? Now, inventory has to be managed. And you want to manage inventory, you want to ensure that you do not overstock. What happens when you overstock? Think about it. And especially if it's a perishable item. Yes, so goods get expired, things become obsolete, right? You lose money, right? Now, on the other hand, if you understock, then it means you cannot meet the needs of your consumers. And of course, consumers have choices, so they will go elsewhere. So apart from losing money, you're losing your share of the market, and that's bad for business. So inventory management is crucial to the supply chain system. Now, inventory management is a practice. It's a practice and of overseeing and controlling the ordering, storage, and use of components that a business uses in the production of items it sells. All right, and we covered that earlier. Now, it also oversees and controls the quantities of finished products for sale. Now, transportation. And as we said, most people, when they hear about logistics, they think transportation. But I want to let you know that logistics is much more than just transportation. However, transportation is a crucial factor in an efficient logistics and supply chain system. So what do we know about transportation? We use transportation every day, right? Now, transportation is a key process in the logistics chain. Why is that so? Now, it is involved at every stage, from the manufacturing of the product to its final delivery. So transportation is needed to take raw material into the factory for manufacturing. Transportation is also needed to take final goods or finished goods to the final consumer or to the intermediaries, the wholesalers, the retailers, right, to be accessed by consumers. Now, transportation is also useful to take workers to and from work, and that's important, right? Now, another important component of logistics. What do you think the other one is? Yes, warehousing. What is a warehouse? What is the purpose of a warehouse? Now, a warehouse may be defined as a commercial building where goods are temporarily stored or rerouted to other businesses. Now, they carry out basically two functions, an inbound function and an outbound function. Inbound, that prepare items for storage. So for example, packing and labeling and even some minor production work such as assembling component parts. So some warehousing are used just for temporary storage, some are used for minor production. So for example, think about a business that manufactures cell phone. It is possible that the cell phones themselves, so the shell of the phone is manufactured by one company, and it is possible that the batteries are manufactured by another company. Now, in order to get, of course, the cell phone is of no use without a battery. So the cell phones could come from point A to the warehouse, the batteries from point B to that warehouse, and the assembling is done there, so you get a complete product to pass on to your consumers. Now, of course, the outbound function is where shipping of goods are done to the final destination, the final consumer. So warehousing is very important. Now, warehousing bridges the time gap between when goods are available and when they're actually needed. So think about it. It's just a few days, can't even say weeks, a few days before Christmas. So businesses already are stocking up on things that they believe consumers will need for the Christmas holiday, right? So these things are available. They're already in storage, especially if they're imported. They're already here until the customer requires them. Now, there are various modes of transportation, and we're going to explore a few of them that are used within the logistics and supply chain operation. Now, what mode of transport do you know of? What mode of transport do you utilize? Write them down. I want to see how many you can list, and then you compare with what we have here. And of course, we're going to look at the purpose of these modes and their advantages and disadvantages. So let's go. Now, road transport. How important is road transport to logistics? Let us explore. Now, road infrastructures are large consumers of space, and we can attest to that. We see the traffic pile up on the roads on a daily basis, right? Now, it is the most commonly used form of transport, not only in Jamaica, but in most countries, and it is considered as the most flexible form of transport. Now, road transport include carrying passengers and freight, such as raw materials, as we mentioned earlier, from producers to manufacturers, as well as between the other elements of the distribution chain, wholesaler, retailer, to the final consumer. Now, the majority of road haulage tends to be carried out by relatively large trucks. We see them on the highways on a daily basis, but smaller delivery vans also play an important role. Now, with the advent of technology and more persons making online purchases, e-commerce has seen a large increase in the use of courier service vehicles. So these are smaller vehicles, they occupy less space, they can maneuver the traffic, and so your delivery can be made on time. Now, are there advantages of road transport? Think about it. What are some advantages of road transport? Write them down. Of course, you want to have your own to compare with what I will share. Now, there are many advantages, but again, because of time constraint, we will focus on the main ones. So I want you to go ahead and add at least 3 more to each advantage that we will look at. All right? Now, it is fast over short distances. So road transport is fast over short distances. It can reach places inaccessible to other forms of transport. Think about that. Now, other forms of transport rely on road transport to connect with terminals such as airports and docks. Because I have never seen an airplane or a ship on the highway, right? They can't go further than the port or the dock, so they rely heavily on road transport to take products to their final destination. So road transport is extremely important. Now, what disadvantages can you come up with? All right, so write those down. Disadvantages of road transport. Now, it is expensive to operate in large, congested cities. Yes, pile up of traffic, not going anywhere, but the engines are still running. That's costly, right? Now, it is subject to mechanical breakdown. And in our Jamaican setting, the roads will also help to depreciate the vehicles. Now, loads are limited in size and weight. So regardless of the size of the trailer that you see on the highway, it has a limit. There's a certain weight and certain size that it is allowed to carry legally. Now, it causes considerable pollution. Yes, all that emission of gases causes considerable pollution. What's our next mode of transport that we'll be looking at? Right, so we'll be looking at rail transport. Now, rail transport is not so common in Jamaica or in the Caribbean, but it is very useful in the logistics and supply chain operations in other countries. So, railways consist of a traced path which wheeled vehicles are bound. I'm sure you have an idea. If you have not seen a train itself, you probably have seen a train track or even a virtual one, right? So it's traced path on which wheeled vehicles are bound. Now, rail is by far the land transportation mode, offering the highest capacity, meaning it can carry tons, heavy weight, carrying thousands of tons. So rail transportation is very useful in carrying large number of cargo. Now, in light of more recent technological development, rail transportation also includes what we call monorails and maglev. So we're going to pause a little and look at these two. They might be new terms to you. All right, so let us examine monorail. Now, the prefix mono meaning what? So the prefix mono meaning one. So what is that telling you? Right? So basically, monorail is a system of rail transportation that consists of a single rail. All right, so as you can see here, oops. All right, go back. I have to go back. All right, so as you can see here, a single rail. So monorail is a system of train transportation consisting of a single rail, typically elevated with the train suspended from it. All right, and then newer technology, maglev train. So maglev, short for magnetic levitation. What comes to mind when you hear that? Magnetic levitation. And if you say magnets, then you are correct. So basically, this type of train consists of two sets of magnets. One set to push the train up, to repel and push the train up off the track, and another set to move the train, the elevated train ahead. Of course, taking advantage of the lack of friction, which increases speed. And for an efficient logistics and supply chain system, speed is important. It's important for on-time delivery. It's important to stay on schedule. It saves time, it saves money, and it conforms to customer requirements. Everybody wants their items to be delivered on time, right? Now, are there advantages of rail transport? Of course. What do you think these are? Write some down. Good? Now, it is faster than road transport over longer distances. So that's one advantage of rail transport. It causes less pollution than road transport. Fuel use is more economical than road transport. And it operates on a schedule, so it avoids road blockages. You know exactly when to expect the train. Good. Now, are there disadvantages of rail transport? Think about it. Based on the advantages, what could be some possible disadvantages or drawbacks of using rail transport? Now, the routes are restricted by railway lines and stations. So obviously, where there are no tracks and where there are no railway stations, then you won't have trains operating in those areas. So it's limited. It is less economical than road for short journeys. So if you're using rail transport, it's best to use it for longer journeys. It is often not suitable for perishable products. And again, because of the long distance that it travels, perishable items might not get sufficient air, even if it's refrigerated, right? Now, another mode of transport doesn't look so familiar, right? Pipelines. What do we use pipelines to carry, though? And I'm sure most persons would say water, all right? So pipeline routes are practically unlimited, and this is because they can be laid on land or even underwater, right? And pipelines transport commodities such as oil, gas, and water. Now, are there advantages of using pipelines? Of course, if we are using pipelines, then the need for environmentally unfriendly vehicles, right? So we don't need these vehicles if we're using pipelines to transport water, gas, or oil. Good? Now, the maintenance cost of pipelines is low compared with other modes of transportation. And cost is important. It's important that a business cut cost. Are there disadvantages of pipeline? How many can you come up with? Now, products that can be moved are limited to liquid, and that's understandable, right? Leakages can go undetected. Remember that these pipelines are under the land or underwater. So these leakages can go undetected for a long period of time, causing wastage and potential environmental damage. Now, another mode of transport, air transport. Now, air transport is the most expensive form of transport, and it is constantly expanding in the volume of passengers and freight that it handles. Now, it is by far the most important method for the movement of people in and out of a country. Now, air transport also makes a major contribution in transporting goods. So even though the main purpose of the aircraft is to transport people, there are aircrafts that also transport cargo. What are the advantages of using air transportation? Think about it. Now, it is the fastest form of transport. So you're talking about speed, you're talking about on-time arrival, you want to think about air transportation. Fastest form of transport, It operates on a timetable, mostly on direct routes. So it's predictable. You can tell, you can give an estimated time of arrival or an estimated time of departure. Shorter transit times reduced insurance cost. So basically, the insurance cost will be dependent on the distance that you're traveling. And of course, there are disadvantages. How many can you come up with? Let us hear them. So high operational cost. And because of the high operational cost, then it reflects in high freight rates. The weight and size of cargo are limited. Of course, you have to consider some form of balance in the air, so you cannot overload the aircraft. So the size and weight of cargo are limited. It is sometimes affected by adverse weather conditions. So any type of weather condition that decrease visibility will affect air transport. And of course, we have maritime or sea transport, a major form of transportation within the logistics and supply chain operation. Now, marine transportation is the most effective mode to move large quantities of cargo over long distances, right? Because of the physical properties of water. So you know that water is buoyant, so it allows the ships to take very heavy load. Now, the main maritime routes are composed of coast, seas, lakes, rivers, and channels. You know, channels such as the Panama Canal and other channels that are used to accommodate ships or vessels. Now, marine transport is linked to heavy industries such as steel and petrochemical facilities. Now, we're going to briefly take a look at some of the main forms of sea transport in commercial shipping, because there are various kinds of vessels and they're designed for different purposes. So let us briefly look at some of these main forms of sea transport in commercial shipping. So we'll be looking at passenger liners, cargo ships, tramp ships, and special freighters. So when you hear of passenger liners, what comes to mind? Passenger liners. Yes, and I can hear somebody actually saying cruising, right? So these are built especially for passenger travel, particularly cruising. By bringing tourists into a country, of course, they provide income from tourism, so that helps to build the economy, right? Now, they sometimes carry some cargo and tend to follow fixed routes and set timetables. What about cargo ships, as the term suggests, right? So the main purpose is to deliver cargo. They tend to operate on fixed routes and regular timetable. Like again, when they operate on fixed routes, you're guaranteed you can have an estimated time of when your goods will arrive at the port, right? Now, they also tend to sail from a port, and this is crucial. They tend to sail from a port even if some of the scheduled cargo did not arrive at the port in time for loading. What does that mean? So it simply means that a cargo ship will not wait on you if you're late, right? Turnaround time for these vessels are very important, right? Staying to schedule, save time, save money. Again, on time, being on time is a crucial factor within an effective logistics system. Good? Now, tramp ships. Have you ever heard the term tramp ships? What are these? What's the purpose of a tramp ship? All right, so these are actually cargo ships that have known timetable or schedule. So as opposed to the regular cargo ship or the liner ship that operates on a schedule, the tramp ship, they have known timetable or schedule. And therefore, they will carry all types of cargo. They can manage to basically any part of the world. Now, these vessels are chartered through a charter party. So it's an agreement between the shipper and the shipping company. To charter, you can charter for just a journey. You can charter for a voyage, right? Now, special freighters. And by the term special, we mean that these are vessels that are built. They are made for special purposes to take special items. So let us look at some examples. So container ships, and as the name suggests, a container ship would take what? So it's designed to take containers, right? Bulk carriers are designed to carry items that are carried in bulk, such as iron, ore, steel, and even grains, things that are not individually packaged, and they're loaded loose onto the ship. Those are referred to as bulk carriers, right? We also have tankers, and we are familiar with tankers. So tankers are used to carry liquid, water, oil, gas, liquid, right? Ferries. What are ferries? Right, so ferries are designed to carry wheeled vehicles. So when we talk about ferries, you will hear the term roll-on or roll-off. So basically, motor vehicles, any wheeled vehicle can be rolled on or rolled off the vessel, and in some cases, they can be driven on and off the vessel. So these ferries are designed to take wheeled vehicles. So these are our special freighters, the main ones. Of course, you can do further research and you can add to this list. Are there advantages of marine transport? Now, as mentioned earlier, the natural buoyancy of water enables ships to carry very heavy loads, which give economies of scale. So that's another new term that we're coming up on, economies of scale. Now, if you're a grade 11 student, you would have been introduced to production. So you should be familiar with the term economies of scale. So what is this talking about? So basically, economies of scale refers to the reduction in the price of producing and distributing a product, so the unit price. Reduction in the unit price, unit meaning one, of producing and distributing a product in proportion to the increased size of the operation of the firm. So in other words, when the firm increases output, then they will enjoy certain benefits. So for example, if a firm starts to invest in technology as opposed to manual labor, it means that now with machines, you're able to produce more in less time. There you're benefiting from lower labor cost. You have less staff to pay. And in addition to that, if you're producing more, it means you need additional raw material. And by purchasing in bulk, you will benefit from certain discounts, right? So economies of scale are basically the benefits of large-scale production. And of course, it aids in international trade, and we can attest to that. Most of the things that we consume, we do not produce them locally, and without marine transport, they probably would not be able to get to us, right? So it's very important in international trade. It causes relatively small amounts of pollution compared to road transport. Now, are there disadvantages of marine transport? Of course, there are disadvantages. Any idea what these are? Write them down. Now, it can carry cargo only as far as the ports, and we mentioned that earlier. So as a result, it's dependent on other forms of transport, such as road transport, in order to get cargo to its final destination. It is a relatively slow method, extremely slow method of moving freight, slow but sure. It is particularly affected by climatic conditions, so any conditions at sea that will can affect the marine transport, similarly to air transport. Now, let us take a brief look at the impact of logistics. What impact does logistics have on a business? Now, logistics can improve competitiveness. And of course, competitiveness is not a bad thing. It means that you have to stay ahead of your competitor in order to survive in business, in order to do well. You have to ensure that you can keep your share of the market or add to your share of the market. You want to ensure that you can provide goods and services at a cost less than that of your competitor. And logistics can help you to do that, or good logistics, I should say, can help you to achieve that. Now, logistics aims to meet the increasing demands of customers at the lowest possible cost. Now, effectively managing the flow of materials, products, information from the supplier to end consumer is all a part of the logistics system. And I mentioned earlier that logistics is closely related to marketing. Here we're conforming to customer requirements. Now, logistics can also achieve what we call comparative cost advantage. What is this, though? Now, comparative cost advantage refers to being able to produce a commodity at a lesser cost than your competitor. And we explored that earlier. Now, how can logistics help? So logistics can contribute to achieving this aim, particularly through what is called outsourcing. Have you ever heard the term outsourcing? What is outsourcing? So let us briefly examine outsourcing. So outsourcing, sometimes referred to as contracting out. We're familiar with that term, right? Refers to accessing goods or services by contract from an outside supplier. Now, it is used by businesses to reduce cost or improve efficiency by relocating tasks, operations, could be jobs, or other processes to an external contracted party. So, for example, a firm that focuses on manufacturing would probably want to outsource their transportation services. So you want to use all your resources and focus on manufacturing. That's what you do best. So in allowing another company to transport your products to your final consumer, you save resources, you save time, additional risk is associated with doing your own transportation. So for example, if the manufacturing firm decides to do their own transportation or offer their own transportation services, it means that they would probably have to own a fleet of vehicles. Now think about it. What are some responsibilities that comes with owning a fleet of vehicles? Of course, you'd have to get drivers for these vehicles. That's more people to pay, right? You will have to insure and maintain these vehicles. Of course, right? So think about outsourcing your warehousing. Instead of owning a warehouse, you allow another business that focuses on warehousing to carry out that function of your business, right? So in that, you save money and you're able to focus on your core activity, which is manufacturing. All right, so this is an example. A manufacturer may outsource some elements of its production to a third party in another country. And when we talk of outsourcing, you will generally hear the term third party. So who's a third party? So when you hear of third party logistics, so third party logistics providers are basically companies that offer any form of logistics services or any service related to the logistics and supply chain. And some were mentioned earlier. So you think about transportation, you think about accounting services, you think about warehousing. Our call centers are perfect examples of outsourcing, where the call centers offer services on behalf of other businesses locally and overseas. Now, the benefits of outsourcing, it can free up cash flow, free up personnel and time resources for the company. It can result in cost savings due to lower labor cost. It enables the company to focus on its core business competencies. And it tends to be directed to organizations who are specialists in the required services, such as a transportation company, right? So our key points for today, things I want you to remember, that logistics is more than just transportation. All right, so remember the definition of logistics. The supply chain is a network between a company and its suppliers. And the key components are procurement, inventory management, transportation, and warehousing. Remember the different modes of transport: road, rail, pipelines. air, maritime, or marine or sea transport. Logistics can improve competitiveness by meeting the increased demands of customers at the lowest possible cost. And logistics can also achieve comparative cost advantage primarily through outsourcing. Now that's all the time we have for CSEC Principles of Business today. Thanks for watching. Up next is CSEC Chemistry.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.
Welcome back to class time. It's now time for CSEC Chemistry. I'm your teacher, Andrea Knight Blackwood. Today's topic is mole concept. Okay, so last week we started the mole concept, and today we're going to continue. All right, so for today's lesson, at the end of the lesson, you should be able to apply the mole concept to equations. You should be able to define the term standard solution. And also, you should be able to perform calculations on mass and molar mass. So, a recap. Question. Jamal has only 11 grams of potassium hydroxide and wants to know what mass of potassium sulfate he could produce if he reacts this with excess sulfuric acid. So here we have three questions. The first one. How many moles of potassium hydroxide does Jamal have? So we're going to go to the whiteboard. All right. So the first thing, when I see a question like that, the first thing I would do is to write my equation, because we need to see what we're working with. All right? So we have potassium hydroxide reacting with potassium sulfate. Potassium hydroxide reacting with sulfuric acid. So we have potassium hydroxide reacting with sulfuric acid to give us potassium sulfate and water. And we know the next thing to do is to balance the equation. So we balance the equation by counting how many potassiums are on this side and how many are on this side. So here we only have one potassium, here we have two, so we balance our equation by putting a 2 here. So we can balance the potassium. So now we have 2 potassium, now we have 2 potassium, so that's fine. So the next thing to do is to balance our sulfate. Now my sulfate ion is SO4, and I have SO4 still intact on the right-hand side. So my sulfate is balanced. I have 1 and I have 1 there. So when we're balancing our equations, we have to remember to balance the hydrogens and the oxygens last. All right, so let's look at our hydrogens. I have 2 hydrogens here and 2 here. That makes 4 on the left-hand side, and I only have 2 on that side. Okay, so I need to put 2 there. So 2 2s, 4. Okay, so the final thing is to balance the oxygens. Now, we already counted this oxygen, so we're not going to include that in our counting. So 2 oxygens here, and we have 2 there, so we're balanced. So let's put in our states. So you know it's 1 mark for our states. So we know that all group 1 elements are soluble. All sulfates are soluble. So putting our states, we must remember our solubility rule. So all group 1 elements are soluble, and of course water is pure, so it is a liquid. So let's continue. It says how many moles of potassium hydroxide does Jamal has? So here we're given 11 grams of potassium hydroxide. So how many moles? How do we get moles from grams? We need to calculate molar mass. So potassium we know is 39, oxygen is 16, hydrogen is 1. So let's add this and see how much we get. That's 56. What is our unit for molar mass? That's right, CMR, grams per mole. So that's 56 grams per mole. So how do I know what to do in order to get mole? First, I look at my units. I must always look at my units in order to get what I want. So the question is asking me for moles, and here I have 11 grams. So what I need to do is to divide 11 by 56 grams per mole, and I'll get my answer. So let's put that in our calculators. Okay, so that's 11 divided by 56, and my answer, I'm going to put it to 3 decimal places. That's 0.196 mole. It is per mole here, and we're dividing, so at the end, it becomes mole. So that is our answer for potassium hydroxide. So we have answered number 1. Let us move to part 2. How many moles of potassium sulfate would Jamal be able to produce? So again, that's where balancing our equation comes in. It is very important to balance our equation. So this is a 2. Let's look at the mole ratio. The mole ratio here is telling me that it requires 2 moles of potassium hydroxide to produce 1 mole of potassium sulfate. So based on that, I am seeing that I used 0.196 mole. So how much of potassium sulfate would be produced? So what I have to do now, it's 2 to 1, so it means that I have to divide by 2 in order to get my answer for potassium sulfate. So I'm going to divide 0.196 by 2, and my answer for potassium sulfate should be 0.098. And of course, it's wrong without the unit. We have to always remember the unit. So that's 0.098 moles. All right, and our final question, what mass of potassium sulfate could Jamal use? So it's asking us for mass. So what is our unit for mass? That's right, grams. All right, so how do we convert from moles to mass? Okay, so what we're going to do, we have to calculate the molar mass for potassium sulfate. So I'll tell you before, the molar mass for potassium sulfate is 174.2. So you can work it out for yourselves. Okay, so I'm going to use the number of moles that I have of potassium sulfate. That's mole. And the molar mass is 14.2 gram per mole. So we have these 2 things and we need to get grams. How do I get grams from this? I am looking at moles and I look at per mole here. I need grams. So based on the units that I have, I know that I have to multiply for these 2 to cancel because they're opposite. So 0.098 mole times 174.2 gram per mole. My answer should be equal to grams. So work it and tell me what you got. Ruth Ann, what did you get? I have to confirm your answer. Let's go. So 0.098 times 174.2, and I got 17 grams. All right, let's move on to what we're actually doing today. So we're going to look at molar and mass concentration. So what is concentration? Ever heard of people saying that that is a concentrated solution? Syrup is very concentrated. What are they talking about? All right, so what concentration really is talking about is the amount of solutes dissolved in a given dissolved in a given volume of a solution. For example, the amount of salt dissolved in water. So the greater the amount of solute dissolved, the higher the concentration of the solution. There are three types of solution. We have dilute solution, we have concentrated solution, and of course we have a saturated solution. Saturated solution just means that the maximum solute is dissolved in the solvent. All right, so we're going to focus on concentrated solutions. So here is a visual for visual learners. So here we have our solvent being blue and our solute in red. Okay? So here, which of these would you think that is a dilute solution and which would you think is a concentrated solution? Take a minute, not a minute, maybe a second. Yes, Siomar, you got it correct. This is a concentrated solution. Why? Because it has more solute dissolved in the solvent. All right, so let's look at our units that we use when we're doing concentration. So remember that concentration really refers to the amount of solute that is dissolved in the solvent. All right, so our solute is normally measured in grams, or we can use moles. And our volume is centimeter cube, which we use a bigger unit, which is dm cube. Dm cube is the same as liters. All right. So here's how we calculate our concentration. Concentration is divided by mass of a solute is divided by the volume of the solution. So our units for concentration is gram per dm cube. Also, if we're using moles, the unit for concentration will be mole per dm cube. And we call this form molarity. We refer to it as molarity, but it's really the same thing. The mass of the solute, which is given in moles, divided by the volume, which is dm cube. Okay, so really, molarity is what chemists use. And when we say molarity, we're talking about molar concentration. And we use the letter M. But it's a big M. So sometimes when you look at your concentrated solution like sulfuric acid in the lab, you'll see the concentration there on it, and you'll see a big M. So the M just means molarity. All right. So let's try a calculation. Let's try one. All right, so 0.5 mole of sodium chloride dissolved in 1 dm cube of distilled water. I want you to find the molarity for that solution, for number one. So, what is the first thing that you think we should do what is the first thing you think we should do to convert this to molarity? Ruthann, is that an answer? Am I hearing the answer, Ruthann, from you? Okay, so what we're going to do, 0.5 moles divided by 1 dm cube. My answer will still be 0.5 moles per dm cube. So that is the molarity for number one. So number two, if we're to do number two, it would be 0.2 moles divided by, we can't divide by 250 because it's in centimeter cube. The unit for concentration is dm cube, so it's mole per dm cube. So here we have 0.2 moles, and we have that is dissolved in 250 cm cube. Now this cm cube has to be converted to dm cube. How do we convert from cm cube to dm cube? That's right, we divide by 1,000. So dividing 250 by 1,000, we move 3 spaces to the left. So 1, 2, 3. And my answer will be 0.25 dm cube. So I'm going to divide 0.2 by 0.25. So what will my answer be, CMR? That's right, 0.8. What is the unit? 0.8 mole per dm cube. All right. Here I have a little illustration right there to show you how to convert from molarity to concentration, from mole per dm cube to gram per dm cube. So to convert from mole per dm cube to gram per dm cube, we multiply by molar mass. And to convert from gram per dm cube back to mole per dm cube, we divide by molar mass. So let's look at this question. 0.2 mole of sodium hydroxide is dissolved in 250 cm cube of water. Calculate the concentration of the solution obtained in units of gram per dm cube. So now we're given mole and we're given cm cube. I need to convert this to gram per dm cube. We just did that a while ago. So how would we calculate it? So 0.2 mole divided by 0.25 dm cube. My answer will be 0.8 mole per dm cube. So we did that just now. So we did that just now, so that's B. So how do we convert from this to gram per dm cube? According to the top, we move from mole per dm cube to gram per dm cube. We multiply by molar mass. And it's given in the question. The molar mass for sodium hydroxide is 40. So we multiply this by 40. And what's the unit? It's gram per mole. So mole will cancel per mole. And my answer will be gram per dm cube. Oh, sorry. Okay. So let's do this calculation. 0.8 times 40. And that's 32 grams per dm cube. Okay, let's continue. Calculate the mass of sodium nitrate to be added in 100 cm cube of water to produce a solution with concentration of 0.02 mole per dm cube. How do you think we are going to do this question? What is it that we're to do? It says calculate the mass. So they're asking us for mass. So what is the unit for mass again? That's right, it's gram. It's grams. So here we have centimeter cube, which is our volume, and we have concentration. So let's see if you can do this question. So here we have 0.02 mole per dm cube. And of course, we're going to convert our 100 cm cube to dm cube. So we divide by 1,000. So having this, we see that they're opposite. So we multiply this by 0.1. These two will cancel. And my answer should be 0.0. Let me do this in my calculator. Not trusting my head right now. Yep, 0.02 moles. All right, but the question is still asking us for grams. So what do we do? Now, the molar mass for sodium nitrate is given in the question, so it's 85 grams per mole. So I need to convert this to grams. So I have 85 grams per mole. So I need to multiply that again so that these two will cancel, and my answer will be in grams. So 0.002 times 85, my answer is 0.17 grams. Yay. One more question. All right, so 0.4 grams of glucose is added into 100 cm cube to prepare a glucose solution with concentration of 0.025 mole per dm cube. Calculate the relative molecular mass of glucose. Now, the relative molecular mass of glucose what is the unit? Now, if we're doing relative molecular mass, we know that we should have something looking like gram per mole. So we need to, what is it that we need to do? We have mole per dm cube, we have 100 cm cube, and we have 0.45 grams. Let's give you a second to think about how to do it. And Ruth, and I want you to do this one for me. Okay, so the first thing we're going to do, we're going to convert our 100 cm cube to dm cube, and then we're going to multiply it by the concentration, which is 0.025 mole per dm cube. So when we convert our volume, which is 100 cm cube, to dm cube, we would get 0.1 dm cube. So multiplying that by our concentration, so 0.025 mole per dm cube times our volume converted to dm cube, that will give us 0.025 moles. And then what do we do next? It is asking us for molecular mass. We have to remember that. So we know that our answer should be in somewhat gram per mole. So here we have moles, and we are given 0.45 grams of glucose. So I want you to pay attention carefully. Look. So here, this is my answer. My answer should be in gram per mole. Here I have moles, and the question gave me 0.45 grams. All right, so I have gram and I have moles. What do I do to get gram per mole? I want per mole, so I know that I have to divide by that. So if I divide 0.45 grams by 0.025 moles, my answer will be 180 gram per mole. And that is the molecular mass for glucose. Okay? All right, let's see if the molar mass for glucose is correct. Glucose is C6H12O6. That means 6 carbon, 12 hydrogens, and 6 oxygens. So my carbon is 12 times 6 plus 12 hydrogens times 1 plus 16 times 6. So let's work this to see what the molar mass is. So 16 times 6 Okay, so 16 times 6 is 96 plus 12 plus 12 times 6 is 72. Add all of these together and I'll get 180 grams per mole. So my calculation above was correct. So let's summarize. Now, molarity is equal to number of moles divided by volume of solution. And the unit for molarity is mole per dm cube. Right? Now, molarity is equal to number of moles over volume. N is equal to number of moles. N is equal to number of moles, while V is equal to volume of solution. So M is equal to N over V. And here we can substitute this equation above to calculate number of moles. So number of moles is equal to molarity times volume to get number of moles, right? So All right, let's do another. So again, let us recap concentration. So concentration is the amount of solute dissolved in a given volume of solution, while a standard solution. What is a standard solution? A standard solution is normally used by chemists, is normally used in the lab. A standard solution is a solution that is accurately known. The concentration is accurately known. So we normally use standard solution to do our titrations. So a standard solution is a solution in which its concentration is accurately known. All right. So let's see if we can answer all of these questions. So you should be able to apply the mole concept to equations, and you should be able to define standard solution, and also you should be able to calculate mass and molar concentrations. And that's it for today's class.